There are two fans in this back-to-back air pulling contest. The large fan has 3 inlets and 1 large outlet. The small fan has 1 inlet and 1 outlet. We strapped the air inlets of these two fans to each other with this transparent connection box. 7,000 cubic meters per hour versus just 3,500. The fan that blows the air out of its exhaust towards the end wins. The timer is running. Start the battle! In the red corner, the large fan is on, blowing air out at 100% power. Wow, that's impressive. The little fan in the blue corner is slowly increasing speed, now around 30%. The big fan is in the lead. All flags are blowing to the left. This is easy for him. We are at 50% speed for Team Blue, and the big fan is still... Wait, what is happening here? The red flags, are they drooping down? No way! The flags are turning. The airflow, it's switching directions. It's switching directions! That can't be. The little fan is at just 65% of its maximum speed, and the large fan is still blasting at 100% power but getting nowhere. Can it recover from this? Doesn't look like it. It's struggling. Look at it shake! All the air is going to Team Blue. The little fan is almost at 100% power. This big boy is cooked. Are they going to switch it off? Someone needs to save the large fan from damage. Total domination. CarbonActive 3500 wins. Wow, that was wild. I did not expect this small fan to win in this air pulling contest from a fan twice its size. Let's switch over to the after-battle analyses by the fan experts.
So, what just happened? The small fan, barely breaking a sweat at 65% power, has just completely overpowered the much larger fan running at 100% power. How is that possible? To understand this, we need to look at the fan performance curves of these two different manufacturers. The horizontal axis is airflow, how much air the fan can move. The vertical axis represents static pressure, how hard it can push. A fan can't deliver maximum airflow and maximum pressure at the same time. It's a constant balancing act between the two. This red line is the performance curve for the large fan. The manufacturer's maximum rated airflow is 7,000 cubic meters per hour, at which point it produces a low static pressure of just 90 pascals. This next curve shows the small fan's performance when running at 100% power, which we'll discuss later. The third line represents its performance at 65% power, at a maximum airflow of around 2,300 cubic meters per hour. To find out why the small fan won in this back-to-back air pulling contest, we can look at the left side of these performance lines. By extrapolating the curves, we get the maximum static pressure at the point of zero airflow. The large fan can generate a maximum static pressure of around 500 pascals at 100% power, whereas the small fan running at just 65% power produced around 525 pascals. It's only slightly more, but that's all it needed to win the battle and reverse the airflow. This was a pure test of static pressure. Then there's the power consumption. At the moment of victory, the small fan was sipping 290 watts. The big fan was guzzling 700 watts. More than double the power, and it was still losing. More power doesn't always mean more performance. As we increased the small fan's power towards 100%, it generated such a powerful negative pressure that it began pulling air backwards through the large fan's spinning blades. This caused huge pressure fluctuations, making the large fan box shake vigorously. To prevent any damage to the large fan, we quickly switched everything off. The point of this test is to demonstrate that when choosing a fan, it's crucial to consider the dynamic relationship between airflow and static pressure. Let's look at the performance curves again. At 100% power, the small fan can produce a maximum pressure of over 1,200 pascals. That's almost 2.5 times more than the large fan's 500 pascals. Impressive. But for typical ventilation scenarios, it's better to look somewhere in the middle or to the right of the curves. Notice the difference in their shapes. With the large fan, a small increase in system pressure causes a massive drop in airflow. In contrast, the small fan's airflow remains much more stable as pressure increases, which is highly desirable in ventilation. So what causes this huge performance difference? It largely comes down to the design of the fan blades. The large fan uses forward curved centrifugal blades, often called a squirrel cage. They're great for simply shoveling air when there's no resistance, but they fold under pressure in systems with filters, dampers, or long ducting. However, the small fan uses backward curved blades. These are specifically designed to generate high static pressure efficiently, making them perfect for maintaining huge airflow through complex systems with high air resistance. Let's consider a practical example. Imagine a facility needs an exhaust system with an airflow of 6,000 cubic meters per hour, fitted with activated carbon filters to remove odors. The owner chooses the large fan box in combination with big filters and straight ducting, thereby keeping resistance to airflow as low as possible. This results in a minimal increase in system pressure of around 125 pascals. Let's add this to the starting point of the fan performance curve. With a system pressure of 215 pascals, the airflow drops from 7,000 to the desired 6,000 cubic meters per hour. Perfect, right? Well, not for long. As the pre-filters collect dust, the system pressure gradually increases by another 75 pascals, to a total of 290. The airflow from the large fan has now dropped to just 3,145 cubic meters per hour, almost half of what's required. The filters aren't even full, yet they already need to be replaced to restore the airflow, driving up operating costs. Surprisingly, if the small fan was in the exact same system at 290 pascals, it would provide a similar airflow. The crucial difference, however, lies in its steep performance curve. This indicates that as the filters clog further and pressure continues to rise, its airflow would decrease minimally. However, there is one scenario where the large fan excels, moving a large amount of air in a low-resistance system. We can follow the system pressure curve of the large fan when it moves 6,000 cubic meters per hour. In that same system, the small fan could only produce an airflow of 3,424 cubic meters per hour at 70 pascals. Clearly, the small fan is not a solution for this exhaust ventilation requirement. So what is the right solution for the facility? The goal is 6,000 cubic meters per hour, even when the filters are nearly full and system pressure is high, like 450 pascals or more. A much better choice would be the CarbonActive 7300 EC fan box. Its performance curve shows it can deliver 6,000 cubic meters per hour while overcoming a staggering 965 pascals of system pressure. Since real-world system pressures for such applications often range between 400 and 800 pascals, this fan can run at a reduced speed, still achieve the target airflow, and have plenty of performance in reserve. Unlike the traditional AC motor in the large fan, all CarbonActive products use highly efficient EC motors. These modern motors offer far better speed control, consume less energy, and operate much more quietly, making them the superior choice for professional applications. A fan's maximum airflow rating is only half the story. The real truth for effective ventilation is matching the fan's performance curve to the pressure demands of your specific system. Get that right, and you'll achieve optimal performance, reliability, and efficiency. In our next video, we'll be conducting more practical tests to help visualize the real-world impact of ducting and filters on different fan types. Be sure to subscribe so you don't miss it.